Hey gang, welcome back to Biostat. Today we're going to discuss the two-way ANOVA, which is still used to compare more than two populations or groups means against one another. But now we're going to be separating these out instead of one factor with like we did with the one-way ANOVA. We're going to be doing it with two. So let's kind of get into it. So as I just said, the two-way ANOVA or two-factor ANOVA is the procedure used when we wish to get two or more population means, or test two or more population means, to see if they differ using two factors instead of just one. All right, so this will kind of like give ourselves like more groupings, if you will. In a lot of ways, the initial part of this test is kind of similar to the categorical test we did called the chi-squared test for independence. We were looking between the two categorical variables to see if they were dependent or independent. The first part of this test is going to be essentially that. We're going to be testing to see if there's what they call an interaction. In other words, the two things affect one another versus they don't. And that'll be the first part of this test, but there's much more to it than that. So some other terminology before we get into depth into those things that we need to go through is something called the word factor itself. I think it kind of makes sense. A factor is something that is something you think might have an effect on your study, but it's usually a controlled variable. Usually it's categorical in nature, but the data it's just helped to divide the data up categorically, but the data is still in this case quantitative. But it's usually controlled by us, the researcher. While we can't control everything about our groups, ultimately we can control how we set up our groups and how we set our study up. And so that's why the factor is something we can control. In the one-way ANOVA we ran a few lectures back now, the drug example that we did, the factor there, or the one factor we had was called, we referenced to as drug type. All right. These factors are then broken down into levels. We called them treatments back in the one-way ANOVA, but another term for that is level. And this is basically just a subcategory of a factor. And so factors can have as many levels as we want. And again, sometimes they're called treatments. In the one-way ANOVA that we ran, the drug example here, our levels were the group on drug A, the group drug B, group drug C. Those were our three levels, drug A, B, and C. And they were subcategories of the overall factor drug type. Okay, so now instead of just having one, we're going to have two factors, not just one. So we might have different levels for the first factor, and a different for the second factor. We'll probably refer to those as factor A and B for the most part, the beginning part of this lecture. There are two formal statistical models, all right, that we discuss, or that we sometimes perform for a two-way ANOVA. Well, the reason I say sometimes perform is the first one of these guys, the first formal statistical model we have to run is what they call the full model of the two-factor ANOVA, sometimes called the cell means model. I will come back to what that means later, or why this is used later when we actually do our example. Or the interaction model, which is the one I prefer. I like either full model or interaction model. This is the one we'll run every time, and this is the one that's a lot like the chi-square test of independence when we're trying to see if the two factors we have an interaction. In other words, do they affect each other or not? And so this model is called the interaction model for that very reason, because we're running an ANOVA to see if there's an interaction effect between our two factors. All right, so is there an interaction? More about interaction in a moment. If we do find an interaction, as we'll see when we go through the steps here shortly, then we run something called the reduced model, aka called the additive model, and I like either one of those terms. They're interchangeable. This is the model we will revert to when there is no interaction effect between our two variables, or our two factors. We'll use the ANOVA output from this model to see if there are significant differences in the main effects for each factor. Another way to think of that last term there is what we're really going to be doing if we use that. When we get to the point where we find there's no interaction between our two factors, we can break them apart and we can see basically for the first factor, are there significant differences in the means between those? That's what they call finding significant differences for the main effects. That's another terminology these folks like to use out there. There's too many terminologies in statistics, and some of them mean the same thing. Wish they would get together and all come to one term, but seems like every discipline has their own term. I'll quit going on about that. And so we need to basically get back to this. We're going to use the additive model to see if there are any significant differences between the means based on the groups in factor A or levels in factor A, or the groups, aka levels of factor B. All right, so we hope there's no interaction effect so we can do this. And so we'll see this played out here in the example later, but also we're going to go more in depth in these things right about now. So the full model, ANOVA, for the two-factor analysis. In the full model, we include some terms. So this is what we would include in our ANOVA output, because when we did the one-factor ANOVA, we called that little variable results, which was just our ANOVA function, AOV. And inside our AOV, we put our response in some of the examples we did, like for the drug type, or the drug interaction effect on the pain scores. We had the pain scores, which was our treatment. That's our Y. Tilde, the drug type. That was our factor. Tilde, factor, the factor. All right. Since we have two factors, we're going to call one of them A and one of them B in this formula. Although they'll have the names of whatever those factors are in the tests that we run. And so you have to include each factor. So you get your response is your Y, or your actual measurements. Then you have your factor A, factor B, and this is your interaction term here. This is the important term that we will leave in there or remove from there depending on whether we find an interaction or not with this thing, interaction term. So the hypothesis for this full model is that either the null hypothesis is that the factor A does not interact with factor B. That's preferably, we would like to not reject the null hypothesis here. But the ha is that factor A does interact with factor B, and if that happens, we have to do something a little bit different or go a different route, as you'll see when we break this down more. So how do we decide p-value wise? Because we're going to get a p-value for this interaction term right here when we run this full model ANOVA. If that p-value is smaller than 0.05, then the factors do interact. So we're going to use an actual cutoff here of being either less than 0.05. If you're greater than or equal to 0.05, then we're going to assume that they do not interact. Okay. Most of the time it'll be greater than 0.05. We never land right on those numbers anyway. But we hope that our p-value is big so that we don't have to reject the null here in most of these cases. But if it is, there's some other things we can do. All right, so what about the term interact? And we've got another definition, a term called additive. When factors interact with one another, say factor A and B, the effect of one factor on our response or our measurement variable does not remain the same for the different levels of the second factor, so factor B. And that's bad. So if the changes aren't consistent across the board between across one if you've got like different levels of factor A, say, and like say we had 3 of them, and the means change in a certain way, but they don't change in that same way with factor B across those same levels, the different levels there, then you get these what we call interactions. And I'm going to show you a plot in a minute that kind of shows more what I'm talking about. But when they interact, that's not always a good thing, because it means one of those factors is affecting the other enough that it's changing the overall averages to interact to where we get this interaction effect. Okay. Now, what we prefer for them to be, so they're easier to deal with, are called additive. And so the two factors A and B, we call them additive if the difference in the population means between any of the two levels of factor A across all the levels of factor A is the same across all levels of factor B, all right, and vice versa, all right. So visually this will make more sense in a minute. Right now, definitionally, this is the formal definitions for these things out there. That may not make a whole lot of sense, but basically we want the changes in the means to stay consistent as we go between one factor and the other. All right, we're going to get averages based on those things. All right, so in other words, factors in A and B can only be additive if, and only if, their mean profiles, in other words, the means for each grouping of factor A level 1, say, and factor B level 1, and then factor A level 1 and factor B level 2, if those things stay consistent as they move from across the different factor combinations. We want them to be parallel. That's the word, as parallel as we can get them. They're not always going to be perfectly parallel, as you'll see what I'm talking about with the pictures we're about to draw or take a look at. So if they are not additive, that means the factors A and B are said to interact, and there's many different types of interaction. And as the images I'm about to show you, what you want to see here is that the profiles need not cross for an interaction to be present. The full model ANOVA p-value is going to really tell us a lot, but we can't always rely on that solely alone when we're doing this kind of a test. This test has a little bit of wiggle room with the interaction, and the interaction, if it's not too severe, we can still do some things with it, okay? It doesn't stop us dead in our tracks when we see an interaction. All right, so we'll go through the steps here in just a moment. But let me talk a little bit more about interaction. Look at this first plot. All these plots are set up very similarly, but you can tell the lines are all structured differently. So this first plot here, where it says no interaction, across factor A down bottom, we've got 4 levels of factor A. 1, 2, 3, and 4. And then we have 3 levels of factor B, and they're referenced by these different colored lines with circles. All right, so factor level 1 is red, factor level 2 is green with filled in dot, and factor level 3 is blue with an open circle. And so notice that the lines here, as you go across factor A from level 1 to 2 to 3, if you go from level 1 to 2, and then you go at factor B level 1, going from 1 to 2, notice that the line's pretty consistently parallel with the line going from factor A1 level 1 to 2 and factor B level. The lines are parallel between factors B level 1 and 2. And then the same thing happens between factor A level 1 and 2. And in between that across all the different factors there, we see a parallel line. As a matter of fact, if we keep going between the next pair of means, those dots represent our means for those pairings. So for example, this red dot right here is representative of the mean of the grouping of factor A level 1 and factor B level 1. So those are the measurements that fit in those two factors. I'm going to show you a breakout of the data we're going to be looking at later of what I mean by the separation of those things. And so, but what's nice about this is it stays consistently parallel from each group to the next. So notice all 3 of these lines here are parallel. And then these 3 lines are fairly parallel, which means it's consistent. That means there's no interaction going on here between these because the lines are pretty parallel. Matter of fact, these are perfectly parallel because I made them that way. So really what's going on, when we see this as no interaction, that implies that this is an additive situation here. In other words, the change from here to here, the number I had to add to get from this mean to this mean is the consistent that I had to go from here to here, and from here to here. So wherever your starting mean is, I have a certain value that I added to it, and I can get the mean for the next level in factor A. Same thing here. This is consistent. So there's an additivity here, and that's why they call it an additive model. We like the additive model because there's no interaction. All right, they're kind of consistent. Now, when you have what they call an ignorable interaction, it's hard to determine whether something's truly we call ignorable or not, because of, you notice these lines aren't completely parallel in this second plot here. But that's not necessarily a bad thing. The ANOVA test will either tell us that the p-value for the interaction term will either be significant or it won't. If it's not significant, then this is probably what I would definitely call an ignorable interaction if we drew a plot of it. Just because these 2 points right here are touching does not mean they're not exactly the same values, because one's just slightly below the other one. Just because they're touching doesn't mean anything. And so that's what I kind of was getting across here. There may be an interaction here, but we may be able to ignore it depending on how small the p-value really is. Like if this p-value for this particular plot here, when we run the full model ANOVA, came out to be something close to 0.05, like say 0.04 something or 0.03, we might can decide that that's an ignorable interaction when we make the plot, if it looks something like this. We may also get a p-value bigger than 0.05 and go, I'm okay with this. I'm not even going to ignore it. I'm just going to say there's no interaction. So these what we call interaction plots I will teach you how to make with the actual data set. But they're used as a tool to kind of further either back up what you see in your full model ANOVA output, or they're also used if your full model ANOVA output's kind of on that borderline, like it's close to 0.05, if you've kind of go, I think that's probably ignorable interaction. So this is not a bad thing here, this ignorable interaction situation. What we call transformable interaction is this third one down here. Notice that these lines are all kind of curved very similarly. That means they kind of have the change in the means between each of these 3 groups for factor B across factor A are kind of changing in a similar way. And so there may be an interaction here, and there probably will become one. But if we did a transformation on the response values, we may be able to make them look more linear. So when that terminology here is not something we will not really work with this in this course. This is more for beyond the scope of the class. It's more an advanced thing. But if we wanted to try to see if we could transform the data to make it look more linear, there's some different ways we could do that if we wanted to. But we're not going to see that very often. We're not going to see that at all in this course. But it does happen from time to time. Not often, though. When we know there's an interaction with these plots is when you see this guy right here. This is a definite interaction. Do you see how the lines cross one another? That's not a good thing when you see the lines cross one another. And so when they cross that badly and there's no parallelness to them whatsoever, that's when your p-value for your full model ANOVA should be rather small. There's a definite interaction going on here, and that's not a bad thing necessarily, but it's just not what we'd like to have. We'd ultimately like to have this guy up here. We'd like something close to this, and possibly this right here. All right, so that's really what we want. We want that. When we get this, it's not the end of the world. There's some things we can do. So what if the factors are additive? Like what if they match up to this first group right here, right? What if they are additive? What does that mean? So if the factors are additive, we can compare the long run mean across the response, so our measurement basically, across any 2 levels of factor A without referencing the levels of factor B at all, and vice versa. So that makes it nice. We can kind of like treat them as 2 separate one-way ANOVAs, if you will, and analyze them the way we did the one-way ANOVA when we find that there's significant differences. So think about, like, you can compare these means here across factor A level 1, 2, 3, and 4
to see if there's significant differences in the means there, using an additive model ANOVA. And then similarly, you can also look across each of these separate lines here, the blue line versus the green line versus the means and the red dots the line here, these three lines here. You can see if the means are significantly different between those levels of B. And so we can separate them, which is nice. All right, that's what we'd kind of like to be able to do. All right. Because of this, we can fit this model more efficiently, and it's actually stronger when we have this case. There are fewer unknowns to estimate for our testing procedure. Not that we're doing that per se, the computer is going to do it for us. But then it means we have more data to use to break down into these two separate groups, which gives us more degrees of freedom for error, which means if we have more degrees of freedom for error, what that translates to is that we have a larger room to make errors so that our judgment calls are probably a little bit more substantiated, if you will. All right. This is basically why the first step in any two-factor analysis, after we've checked our normality assumptions and our variance assumptions for the full model, is often to see if the additive model even fits, aka do a test for interaction, and if there is no interaction, then the additive model will fit. All right, so that's usually the first step in all these things. We're going to run through the procedure here in a minute, and it will be daunting at first, but here's the procedure in a flow chart. The one thing I wish I could change, but I did not create this flow chart, probably need to recreate it myself, is here. My grad professor liked to use 0.15 as his cutoff for interaction versus no interaction. We're going to use 0.05. We're going to be a little more stern about that and be a little bit more cautious and not as lenient here. So we'll use 0.05 as the only difference here. But instead of reading this chart to you verbatim, I'm going to actually go through this chart in the next couple of slides. All right, and we're going to go through and do this stepwise of what goes on. Okay. So step one, regardless of which way that flow chart goes, is to check the following assumptions on our full model. In other words, all the data, the similar kind of things that we did when we did a one-way ANOVA. So we're going to have box plots for both factors. All right. So when we create them this time, we'll have one for factor A and one for factor B, and we'll be able to look at them similarly. Like they'll just be two separate graphs, but we'll look at them similar to how we did in the one factor ANOVA. We'll get a single residual versus fitted plot. So we'll be, again, looking to see if the variation's similar or we see a pattern emerge in that plot. We'll look at the residual QQ plot for normality and see how normal we think the data is. And we can also do the Levene's test for homogeneity on these groupings. And the thing to kind of note here is this test, the Levene's test, will not work if you only have one or two measurements per treatment combination. I'll show you what I mean by per treatment combination, because we're going to run into this very issue today for only having two measurements per treatment combination. In this case, we can rely on the residual versus fitted plot to determine or to see how comfortable we feel with the variation. All right. But if we have more than two values in each combination, then this Levene's test usually will work well for us. It should back up what our residual versus fitted plot tells us. Okay, so we'll do those. Step two is we're going to fit the full model ANOVA, all right, for the interaction between factors A and B. The full model, we include, again, both terms that we have our response, the term for factor A, whatever term for factor B we have in our data set, and then we take the term for factor A and multiply it times factor B at the end, so we have to put this little thing in our ANOVA function. All right, and it will spit out for us a p-value for group A, for factor A, one for factor B. We will not read those here. Some of you may have been taught in another class to do that. We are going to do this by the book. You don't do that here. It's not a big deal if you do, but at the same time, it's not how you're supposed to do it.
sometimes that can you can get into some trouble with that. But the interaction terms p-value is the one we're really going to be concerned with. The hypotheses for the full model again are HO, the factor A, does not interact with factor B. We kind of want that. We kind of want to not reject the HO here. And then the HA is the factor A does interact with factor B. So we'll fit that model to see if we have an interaction. All right. And so step 3 is, depending on whether we have an interaction, we either do one of these, we either do what's going on the left-hand side, or we'll do what's going on the right-hand side. So on the left-hand side, if we have no interaction, in other words, we do not reject HO in the full model, I'm going to start calling it full M. All right, if, in other words, if P is bigger than 0.05, then we're going to remove that A times B term in our ANOVA model and rerun the model to get the correct p-values. All right, this will correct the p-values a little bit when we remove that term. They won't change them much, but there's that once in a while where you're close enough that it'll change the p-values enough to where maybe they would not be significant when they should, or vice versa. And so our model, our ANOVA model in the ANOVA function will end up putting the response equals just factor A plus factor B. We just remove that plus A times B part up from it. Okay. And so we'll rerun that, and we'll get p-values for factor A and a p-value for factor B. We'll be able to see if they're, just like in the one-factor ANOVA, we'll be able to see if those things are significant or not. All right, and if they're significant enough, then we have then we know there's a difference in the means for a factor A. If there's the factor B's p-value is small enough, then we'll know that too. So we're going to talk about those on the next slide. We call those the main effects. We're going to so when we run this, we call it the additive model. This is called the additive model, or I'm going to call it ADM for short. It's the effect of one of our independent variables, in other words, our factors, on the dependent variable, our response. And so we're going to see the next slide before moving to our step 4 on what we need to do to officially do this test here. All right. If there is an interaction and P is less than 0.05, in other words, we reject the null in the full model, we'll retain that full model ANOVA with the interaction term, so we'll keep this guy here with the A times B. And in this case, we'll skip the next slide that I'm about to go over, and we'll see step 4. So we'll come back and talk about what we do next with this in a moment. Right now we're moving on with this stuff over here on the left-hand side. So to test the main effects for A and B doing the additive model, we have hypotheses for the additive model for the test for the main effects. All right, for both one for factor A, one for factor B. These are done at the same time, but we treat them like they're separate things, even though we're doing it at the same time. So the factor A test and factor B test both have null and alternative hypotheses that are like our one-factor ANOVAs, almost exactly, with the exception of the symbology. And I want you to make sure you pay attention to the symbols here. I don't care if you use a capital T instead of the Greek letter tau when you write these up, or you use a B in place of these, as long as you're using some kind of thing that looks like a symbol here. But just like our one-factor ANOVA, we're still seeing if there are differences in the means. And so for factor A, we're looking across the different levels of factor A. And in most textbooks, they use the Greek letter tau instead of mu here. And however many groupings you have or levels you have for factor A, you're going to say that they're all equal. And the HA is at least one mean differs for factor A, whatever the factor A happens to be. For factor B, we use the Greek letter beta, and again, it's the test for HO. All the group means are equal across the board. And the HA is at least one of those means differs for factor B. All right, so again, I'm using tau and beta because we have two different tests we're running at the same time. So to differentiate between them, I'm using two different groupings here. In a scientific journal or something like that, yes, you can get away with writing these things out in Word. The mathematician in me wants you to use symbols for these things, so I'm going to be picky about that, just so you know. So if there are important interactions in our full model, these two main effects tests that I'm doing above can be highly misleading. All right, it's kind of like averaging apples and oranges. You don't want to do it because it makes no sense. So if you do have important interactions or substantial ones, you don't want to do what I'm doing on this page. You don't want to do these two-factor tests and then look at the p-values to see if there's significant results. And it's basically kind of assumed across the board that when you do have a substantial interaction, that you don't compare the main effects of A or the main effects of B across their levels, because it could be, you can get into a little bit of trouble. You can do it still, but you can get a little bit of trouble. So we'll talk about that here in a minute. So step 4, of course, is just like the last thing we did after we found the significant result from our one-way ANOVA. If factor A has a significant result and or factor B has a significant result, whichever ones are significant once we run our additive model. So this test here, factor A and B tests, when we do the additive model version, if those are both significant, we're gonna do multiple comparisons on both groups separately. If only one of them is, we're only going to be concerned about the one that's significant. So, and sometimes you might find that neither one of them are significant. It's possible. But if there are significant p-values for either factor A or B in our test of our main effects, we're going to run our multiple comparisons using Tukey's HSD method on the significant factors only. All right, so if factor A was the only significant factor between it and B, then we would only run Tukey's HSD on factor A. If they both are, then we'll run Tukey's on both. So basically that is, we'll run the multiple comparisons for A if it is significant separate from B and vice versa. All right. So again, this is still in that, the left-hand side still representative of that we do not reject the hoe in the full model. Okay. If we do reject, again, the hoe in the full model, if you kept the full model, all right, are the interactions ignorable? So this is where making that interaction plot kind of comes in handy. If there's definitive crossing, like we saw in the fourth plot on that slide earlier, they're not ignorable. We can't ignore that. But if they're mildly crossing just slightly, and it's not as bad. I mean, when they're almost perpendicular to each other, the lines, that's pretty bad. That's a big interaction. So if you think that these interactions are ignorable, and you got to be very careful about this, you can assess the main effects for A and B just like we did on the the left-hand side when we do not reject the hoe of the full model, all right, and do the Tukey's HSD. I don't recommend doing this because you're kind of putting a lot of pressure on yourself, and you could be telling people things that aren't true. All right, what's kind of preferable to do is this last little bit here, and I will do an example of this, not today, but I will do it in the next on Wednesday's recording. If the interactions are significant, we can perform Tukey's HSD method by keeping the full model, but only looking at the interaction terms, the A times B terms. In other words, we won't look at A separate from B like we do over here. We'll take and look at just the A times B terms, and what we'll do is we'll basically get p-values and confidence intervals for every combination of factor A mixed with factor B. All right, you won't see that today, but I'll show you an example of what that means. That it kind of the confidence intervals get really nasty. All right, and sometimes it's hard to discern things. You can still interpret your confidence intervals or your p-values in the same way we've done every multiple comparisons we've done with one factor ANOVAs and the way we'll do them today, but it's going to be, the setup's going to be much more difficult to look at, just so you know. Again, we'll look at that later on. So let's actually get into an example of doing this whole procedure we just discussed, and see how it's done. So in the experiment I chose today, it was conducted to determine if the effects of 4 different pesticides, we'll call them P1 through P4, on the yield of a fruit from 3 different varieties of citrus tree. We'll call those varieties V1, V2, V3. I don't know exactly what they are. The study didn't tell me exactly what the varieties were of the citrus trees. But 8 trees from each variety were randomly selected from an orchard. The 4 pesticides were then randomly assigned to 2 trees of each variety, and applications were made according to recommended levels. All right, so we don't know how much they put on these trees. That could also be an underlying factor in these things as well, if somebody screwed that up. The measurement, or our response here, is the yields of fruit measured in bushels per tree, were obtained after the test period. The data code below can be copied, and we copy the data into R. So I've already done that over here because we're going to run through this in R as well. But let's look at what the data set looks like right now, because this is kind of what a 2-factor ANOVA data set should basically look like. I have my yields, my bushels per tree values here. So how many bushels of citrus I got from the trees during the test period. And then here, pesticides factor A and variety is factor B. And so pesticides broken down again into P1. So the first 6 trees here have P1 next to them. And then they're broken down by variety. So those 6 trees got P1s, and then there's variety 1, 1, 2, 2, 3, 3 for the different varieties of trees. So there's 2 trees got a variety 1 got pesticide 1. We've got down here 2 trees got pesticide 2 of variety 1, and so forth and so on. So there's 24 trees total, and they were just broken down this way. So there's 8 trees of each variety total. So if you count up the number of V1s are, there should be 8 of those. That's what that was referring to in the problem over here, when it said 8 trees from each variety were randomly selected. Okay, and so we've got that. So R will know how to deal with this based on the way we've got our factors labeled here. Okay. So the first things we need to do is, step 1 is we need to check our ANOVA assumptions. We need to make sure they're met. So we need to look for the data being normal with a somewhat common variance. The sample treatments are also need to be independent based on the design of the experiment. In this case, they are. They were randomly selected trees, and so the trees are independent, and they're from different orchards, so they're not the same tree. It's one of the beautiful things about biological examples is oftentimes you're talking about different entities or different items or individuals or living things, and so those are definitely independent from the next. There are some things that can make certain living things be dependent, but in these cases they're often independent, which is a good thing. So we're going to create our box plots. We'll create the residual plots in QQ normal, and we'll run the Levine test. All right, so that's step 1. So the next couple of slides will just be that. So I've got my par MF row C1 and 2 because I wanted both of my plots to show up in the same on the same output, if you will, instead of putting one after the other. And so when you run this in R, I kind of want to do these in R as well to show you what happens today. You can get sometimes some error messages. So I put my par in matrix frame row C1 and 2, so it's a 1x2 window, so I put 2 side-by-side graphs. My plot command I put a little bit different than I did before. Notice I have yield
was my response value of where my actual measurements were at, the number of bushels per tree. Factor A was pesticide plus factor B, which is variety, plus factor A times factor B. You got to put it in there that way when you do the full model ANOVA anyway. So this is the structure of the full model ANOVA. But in the plot command, this will actually build you 2 different box plots. Data equals citrus. Since we attached it, I don't know if we need to include that in there, but you guys will probably most likely be working with more than one data set when you're working on these projects. It's good to tell it exactly which one you're working with. And then the colors, I chose 2 through 5 because I needed 4 colors for factor A in this case, which is the pesticide factor, because it had 4 pesticides we were using. So I chose to make sure I got 4 different colors. So anyway, when I hit enter here, it's going to say hit return to see the next plot. In other words, it's behind the scenes, it's already plotted the first box plots for pesticide. But if I hit enter again, it will pop up there and I'll get the pesticide box plot right beside the varieties factor box plot. Okay, so I'm going to come back over here and we're going to look at it in R. Not bad looking plots overall. There's some skewness going on between some of the groups, but some of them aren't terrible. So I'm kind of happy about that. You can definitely tell there's probably going to be some differences possibly. We can't guarantee that. The pesticides, pesticide 2 and 4 look a lot different from pesticide 1 and 3. Therefore, there may be some significant difference. Maybe pesticide 2 and 4 yields more fruit, keeps more bugs off the fruit. Therefore, we're growing more fruit than pesticides 1 and 3 do, but we won't know that until later for sure. And then the yield of the number of bushels we have per tree for the variety type looks like there's going to be a significant difference. It looks like tree variety 3 produces a lot more fruit just from looking at this plot than variety 1 for sure, but we don't know if it's significant enough to be different from variety 2. Again, we'll see that later in the test if we find significant results here. Again, we can't go off of this to discern that, but we can look across and see how normal the plot looks, and I'm not too worried about the normalcy or the variation here. The variations do differ quite slightly here and there, but overall it's not terrible. I've seen worse. Okay, I've seen a lot worse. Next, we need to do our residual versus fitted plots. I'm kind of okay with these as well. We'll analyze them a little bit more here. The normal QQ plot does look like it's trying to curve. It almost looks like it's 1/2 of a normal curve if you just connected the dots. But if you remove the outliers, it's not a bad looking plot. It's curving slightly, but it's not what I would call a hooker. So I'm okay with that. The residual versus fitted plot, I'm actually okay with that as well. That doesn't look too bad. The spread's not exactly 100%. I'm not 100% crazy about it, but again, the problem with this data set is we only have 2 measurements for each grouping variable. And what I mean by that is this. What you're seeing here, let's create it in R real quick. I want to show you something you can do. I didn't color my points, but you can do that. To first of all, remember this is where we actually create our first full model ANOVA. So I'm going to call it full M. I recommend you guys do too because it kind of helps keep you on track. And then we'll use this again here shortly when we run our full model ANOVA summary to see what our p-values are. But to get our plots, we need that in there as well. So that'll be the first thing we pop in there. And then we can do side by side of the plots we have. So full model ANOVA, again, there's that measurement yield, tilde, factor A, pesticide, plus factor B, variety, plus the interaction term, variety times pesticide. It doesn't really matter what order you put those 2 in, you'll get the same result. It's multiplication. And then data equals citrus. And then down here for plot full M, that's how we'll get this. It's just like when we did plot results for the 1 factor ANOVA. And then C1 and 2 will give us the 2 plots we have over there.
And then the PCH, I just wanted them to be filled in circles. The color equals cyan 3. There's an alternative way to color these if you want them to be colored like the based off of the grouping factor A and B groupings. And the way you would do that is right in here, instead of color equals cyan 3, you could literally put pesticide. Let's hope this works the first time I do it. Not resticide, but pesticide. And colon variety. And when I do that this time, they should be colored, yeah. And so it makes this multicolored thing. I actually find that with with these two-factor ANOVAs, it makes it look a little more confusing, especially when there's only two. Matter of fact, let's zoom in on this. You notice there's only two yellow dots. There's two green dots here. There's two red dots here. They're slightly different red than these two here. It's hard to see on the screen. There's two gray dots, two black dots. There's another two black dots. Those black dots and these black dots don't match up to each other. They're not the same group. So every two dots you see in a vertical pattern are different pairings of factor A and factor B combined together. All right. And so when they're colored like that, I actually find that harder to look at. But you can do it. It doesn't matter. It's totally a preferential thing on the part of the person doing the research. But again, I don't see a great deal. There's different variations here. It's kind of going to be hard here to sell us on the fact that there is different variation here between the spreads at these points, since we're looking at, vertically we're looking at two of these match each other. So for example, this guy and this guy are the same match here, and then you got this guy and this guy, and so there's a difference in spread here for sure. But the problem with it is we don't have enough data here to really say that the variation here is drastically different. So when we run the Levine's test, it'll back that up for us. And how I know for sure, when I say that they're pairing, I'm going to break out of this for just a second and show you the actual raw data. When you look at it, I've got pesticides 1 through 4 across the top is the rows, the variety 1, 2, and 3 across the bottom, and the numbers from the data set, there are literally two values in every one of these cells. So that when I was referring earlier to the cell test across cell means or whatever I said, whatever terminology I used earlier on, that's what this was meaning. There's only 2 items in each one of these cells. That's not a really good thing. So this study should have been a little bit bigger, should have had more data in it. We really like to have more in each one of these combinations. So the 49 and 39 right here is the combination of pesticide 1 with tree variety 1. The 50 and 55 pesticide 2 with tree variety 1. All right, and so when you have those combinations, as we're talking about here, of the data with these two factors, then you kind of have to, you want it to be more than 1 or 2, because you end up running issues with looking at the spread, because the spread's going to be different if you only have 1 or 2 things in your data set for each of those combinations. Not a good thing to really to deal with. So let's get back to the page we were on. All right, so we were right. Yeah, all right. So again, I don't have a huge issue with the spread. I don't see any specific patterns, but I'm not 100% loving the residual versus vitta plot either, but I'm okay with it to a certain extent. All right, we'll see better ones when we have more data. So looking at the box plots, as I said, the pesticide group box plots seem to show a consistent spread for the most part, with the exception of box plot 4, which may have seemed a little skewed to the which may be a little bit skewed for sure. So if you look at the first one I'm talking about, this box plot here is definitely more skewed than the other 3. The other 3 I would call kind of approximately normal, just based off of the way the whiskers are coming off of, but this one has a much longer whisker on the top side, which means it would be right skewed. It also appears that pesticides 2 and 4, as I stated when we were looking at that, may differ from pesticides 1 and 3.
All right, there may be a significant difference there. The variety box plots, there is less consistency with the spread, although each box looks to be approximately normal. And it's, when you look at them individually, but there may be a difference between each of the group means for each of the three varieties. Depending on what kind of trees they are, that kind of makes sense. And the residual versus fitted plot, it's not a bad looking plot, like I said. There are some slight differences in variability of the points as you move from left to right, but there's no clear pattern or trend that leads me to believe that the variances are unequal. So the way it's spread out is kind of monotonous and just kind of like bland. There's no shape to it. It literally looks like somebody took a shotgun and shot a piece of paper from a certain distance and just left random holes everywhere. That's kind of not a bad thing. So that leads me to believe the variances but there's no clear pattern or trend that leads me to believe that the variances are unequal. So I think that we are okay assuming the variances are roughly equal here. The normal QQ plot, like I said, most of the points fit close to the line. There are a few potential outliers, but those points don't concern me too much. I'm okay with the normality of this to a certain extent. It's roughly approximately normal. Let's put it that way. It's not the worst plot QQ plot we've seen this semester by far. So running the Levine test to round out step 1. When you run it in R, I'm not going to run it in R here because I'm going to get the same thing, but I did take a picture of what you'll get. So remember, we have 2 measurements per combination. Because of that, we're going to get this warning message down here when we run a data set like this. Look how small that flipping p-value is. It says it's less than 2.2 times 10 to the negative 16th power. That's basically 15 zeros out in front of that first 2. And also the F value is astronomically huge. That's 2.4 times 10 to the 31st power. That is a big, big number. When an F value gets that big, it's trending to infinity. And that happens, and that's why we're getting this warning message, because when we have only one data value per combination, or 1 or 2 in there, we end up getting these huge F values because there's not a lot of variation in there to tell the difference. And so it's saying you might want to rely more on your residual versus fitted plot to see how well you think the variances equal one another. And you can disagree with me on what I said about the one earlier. I'm fine with that. I mean, I don't mind a disagreement on these things. There's a subjectivity to analyzing residual plots. Doesn't necessarily mean, and there's also an art in it too. So the conclusion here is, if we go by the p-value here, then we'd say the variances are unequal. But with that warning message popping up below, says that we probably should take that in mind, and says the means we don't have enough data really to get an honest conclusion here, and therefore we will rely on the residual versus fitted plot. So I'm okay with this one. We'll move on. I'd like for the people who did this study to go back and get more data. So step 2 is we have to fit the full model, ANOVA, to test for see if there's an interaction between factors A, pesticide, and factors B, variety. All right, so the ho here is there is no interaction between pesticide type and tree variety. And the ha here is the pesticide type and tree variety interact. Simple as that. So when you run your full M and R, it's very much, we already ran it once before, but again, it's yield, which is our measurement variable, aka our response, tilde factor A pesticide plus factor B variety plus factor A times B pesticide times variety, and then we just need to run the summary function on that full M that we built earlier. Since we already built that earlier, you don't have to type that in twice, but summary of full M, full M, and it gives us this. And the only p-value we're concerned with right now from that is the one that's for the interaction term, which is the pesticide variety. So we're really looking only here at this term when we do the full model.
And then we're looking over here to see, is this smaller than 0.05? Well, that's not. That's a lot bigger than 0.05. As a matter of fact, even if we had chosen 0.15 as our cutoff for rejecting or not, we still wouldn't have rejected. So since P is bigger than 0.05, we won't reject the full model hoe here. There is no interaction between the pesticide type and variety. All right, so we're sticking with what the hoe's claiming. We can run the additive model to test the main effects of the factors. So now we can look at factor A, which is pesticide, separate from factor B, to see if there's any significant results. Based on these two p-values given for those factors up here on the full model ANOVA, notice that this one's 0.00011 and this one's really small, closer to 0 here. So they're both smaller than 0.001. But those are going to change slightly when we change to the additive model, which we'll do next. All right, so before we do that, let's run this is what the interaction plot for this would look like, and I kind of want to go through the function here to talk about what's going on in the interaction plot. All right, so I'm going to plop it into R, and then we'll talk about it over here. So the interaction plot stuff, and again, I went through the R code only text file and filled all this stuff in there for you as well, so it's there to help out and as notes. And so to run that interaction here, let's get my data, my code here. Let's talk about what goes on in the interaction.plot function. This has got a lot of stuff going on in it. I'm going to go ahead and hit enter. If you're running this in your console and you get this, your image down here pops up where it's still trying to do a two side by side ones here, you can click the sweep button and then rerun the function, and it will put it all in one window for you. But since you're doing it in R Markdown knows to reset that every time you start a new R command little prompt, a little code chunk in the R Markdown. But let's look at what's going on inside of it. The first input will be your factor A or your factor B. I'm going to show you in a second, and that's why I didn't change my plot output over there yet. And the second one's a variety or factor B. So it's usually factor A, factor B, the measurement variable. You put in the rest of this stuff will pretty much be almost the same with a few changes. You can basically copy and paste this and just change these first three things in some of the, like the main title and the X labels and Y labels. You can change those things. But the function equals mean needs to be in there because we're doing means here. The type equals B will make sure that you get the various different lines in different colors. Also, not necessarily different colors, but you'll get them in different contrasts, like the different dots and the different circles. And also you'll get lines with the points. Legend equals true, so you can see your factor B stuff in there. In the case of this one, that's variety. It's factor B, and factor A is down here across the bottom, pesticides. And then you can label your X label accordingly as pesticide, name it factor A. It doesn't automatically do that. Y label, your yield value here. In other words, Y label is going to be your measurement variable name. PCH C1 through 19, I'm kind of giving it an option to pick different values for the points here. And then the color, again, I knew how many levels I had in my second factor, so I needed 3 colors, so I've chose 2 through 4. Change the line width to 2. Basically copy and paste this, change a few things around, and you'll be good to go. Now, what if I flip-flop the factor A and B together? I want you to see how what the difference is here. So if I take variety and move that in front of pesticide, then that means that variety is going to be, I'm going to have 3 V1, V2, V3 across my x-axis. So my X label should now be variety. All right, and the Y label can stay yield, but everything else will pretty much stay the same. I should have 4 colors now instead of just
3, so I'm going to change this as 2 through 5 to give myself the 5th color here on the plots, on the colors of the lines. And when I hit enter, I get a much different looking thing, and it's harder to read. One of these factor A or B, when you reorganize them, one of these will always look better than the other. So if we zoom in on this real quick, and our full model ANOVA's p-value was big enough we didn't reject, and we said that there's no interaction, right? Well, looking at the plot here that I like, you can see that these are roughly parallel. None of these guys are crossing each other. They're not really getting too close to one another. And so depending on which way you set these up, it often will look better than the other. So sometimes you might want to try the different, or rotating the factor A and B's around in the interaction.plot function. Because over here, what's funny is that across variety 1, 2, and 3, if we look here at, and it's running off the page because there's not enough room here. But looking at this is P1, P2, P3, P4 going up through here. So across the pesticides, the groups are roughly parallel. Like I said, this is kind of like where you'd say that was an ignorable interaction. The red line touching close to this dark blue line. They're roughly parallel. It's not the worst thing I've ever seen. But then the green line is crossing at one point, all right? But it's not quite perpendicular, right? And the green line actually follows suit with the other two pesticides. So remember how when we looked at the box plots and I said that pesticide 4 was a little bit skewed, right? This is the effect of that. So it's kind of changed direction. It's almost like it's flip-flopped on itself. This doesn't mean, again, that there's an interaction. It just means that there's a possible interaction, and you would almost call this ignorable because it's only crossing once, and it's also not the crossing is not very perpendicular. So the other 3 lines are rough, but they're okay. So you don't have to give me both of these. Give me the one that looks best to you in the output. There's always going to be one that looks better than the other. And in this case, it's better to look at P1, P2, P3, P4, and then look in this case, and then have variety 1, 2, and 3 along your be the different colored lines. Okay, and so you'll notice again with pesticide 4, look at the spread out, the way that these points spread differently from between the 3 groups for the variety. It's a little bit different, right? They're like these two are kind of close together, while the green dot and the red dot are way far apart, versus where it's kind of flip-flop for all the other pesticides. The pesticide for 3, 2, and 1, the points between the red and the green are all kind of close together, are closer, but then the distance between that and the blue are way far apart. That's telling me again that pesticide 4 probably has some issues in its normality. But again, we're talking about 2 data points to get a mean. There's issues there with this data set. This probably wasn't the most well thought out study. So, but again, go with this first plot. I just wanted to show you the differences between them, and I'll quit going on about that now. All right. All right, so let's go continue on so we can. So we found that there was no interaction. We're about to run our additive model now. All right. So since there is no interaction, we run the additive model. Again, I called that add M and R. And the difference between the additive model and the full model is, remember, the full model equal the analysis of variance. And in this case, it was yield tilde pesticide. I'm just going to call it pest plus variety plus pest, not pet, pest. Come on, man. Pest times variety. All right. Data equals citrus. So when I was mentioning earlier, we're going to remove that. Since there was no interaction, we're going to remove the interaction term. We remove that here. Okay. And so that's gone out of there. So we're just doing pesticide plus variety. All right, that's the only thing we really changed. And then I do summary add M. And you notice I have no interaction in my row in my table down here, but I have one for pesticide, for the main effect for pesticides, and the main effect for variety. And when we look at the p-values, these are, yes, still significant, but look how much more significant the p-value for pesticide is now. That's a lot stronger case than the one we had before. Is that meaningful in the long run? We're talking about like minute, not minute differences. This is much smaller. 6.3 times e to times 10 to the negative 5 is a little smaller than 0.00001 or 0.0001. And so this is just saying we have a stronger case to reject the hypotheses. So let's run our we basically ran our hypothesis tests here for both pesticide and then one for variety. So the way you write that up is on the next slide. So factor A, the pesticide test, when we were looking at the output a minute ago, we've got our null hypothesis. Since we had 4 pesticides, the mean for pesticide 1 is equal to pesticide 2, is equal to 3, is equal to 4. And the ha is that at least one of the mean yields mean yield differs among the 4 pesticides. All right, probably should have put citrus mean yield. And then the conclusion, since our p-value was definitely smaller than 0.001, we reject Ho. There's very strong evidence that at least one of the mean yield differs among the 4 pesticides. And factor B is a similar thing, but you have to do it. And you only do these if they're significant. If they're not significant, then it's, you can do this conclusion right up here, but you don't have to do the step 4 part. You only do the step 4 for the ones that are significant, as we'll see. Since both of these are significant, we're going to be doing them for both. But here, the Ho is that the mean for variety of tree type 1 is equal to the mean for variety 2, which is equal to the mean of variety 3. And again, the Ha here is at least one mean yield differs among the 3 tree varieties. And since the p-value is smaller than 0.001, we're going to definitely reject the Ho. There is strong evidence, and matter of fact, very strong evidence, that at least one mean yield differs among the 3 tree varieties. I'd almost say with p-values as small as the ones we got here, there's some hellacious evidence there that there's a difference between these groups. Okay, so since there was a difference in both of them, we needed to perform Tukey's HSD to perform multiple comparisons for both factors to see which groups are significantly different. All right, and so we're just do Tukey's HSD here. We won't do the pairwise.t.test on these. Because we'll get the same results either way. So the main effects for factor A when we run the Tukey's HSD is I still use my additive model, all right, add model, all right, and we do pesticide in a single quote or double quotes, it doesn't really matter. And so it's only going to give me the confidence intervals and p-values for the pesticide factor. And if we look through it, we'll see the following p-values are significant. So we've got significance here for P2 minus P1. We've got a significant factor here for P4 minus P1. Significant here for P3 and P2. And finally, a significant one for P4 versus P3. All right. And again, remember the order of these things make a difference in which one has got a higher mean yield than the other. And since P2 minus P1, and you got positive lower and upper bound for your confidence interval, that means pesticide 2 was higher overall in citrus production than pesticide 1. We also know that pesticide 4 was both of those values are positive. So pesticide 4 was better than pesticide 1. It's kind of what we saw in the box plots when we saw them again. The next significant one is P3 compared to P2. And since these are both negative, it means that P3 Both endpoints are negative. P3 is smaller than P2, therefore P2 is larger than P3. We talk about it as in terms of P2. So here P2 was better than P1. Here P4 was better than P1. Here P2 is better than P3. And the last significant one down here, P4 minus P3 are both positive, implying that P4 is better than P3. So it looks like pesticides 2 and 4 did a better job at producing mean citrus yield on average than pesticides 2 and 1 and 3. And so we can conclude that along with interpreting our relevant significant intervals here. So again, I'm not going to read this whole thing out to you. I'll read one of them, but they all follow suit. So we analyze the Tukey output. At any interval less than 0.05 is significant. In the output, we see P2 minus P1, P4 minus P1, P3 minus P2, and P4 minus P3 are all significant. So we should interpret the intervals that we saw as follows. Again, that blanket statement with 95% confidence, all of the following hold. The mean citrus yield under pesticide 2 is larger than pesticide 1 by at least 2.89 and at most 26.78 bushels per tree. And that's exactly what we saw here, by at least 2.8 or 2.9 and 26.8. Or you can go to 2 decimal places like I did here. It's really up to you. And then you just kind of go through and do that. Now, if you have more than 4 significant ones, I'm probably not going to make you give me all of them. I'll let you pick 3 or 4 of them, but I want you to kind of give me an overall conclusion like you'll see at the very end of this. Some little statement saying what you found. All right, so I won't go through the other 3. I think that most of you should be able to make sense out of this. The one I wanted to definitely point out was the one that had negative values for the lower and upper bound, which was this guy right here. Since they both had negative, you need to talk about this in terms of P2. So the third interpretation I have here should say the mean citrus yield under pesticide 2 is larger than pesticide 3. We never talk about being smaller than, we talk about the one that's larger than. Pesticide 3 by at least 4.72 and at most 28.61. 28.6, what I say, 28.61 and 4.72. So 4.72, 28.61. So just pay attention to that. Don't mix those things up. It's easy to do. So we've done that. Now that was just on factor A, the pesticides. We also have to do factor B, look at the main effects for factor B on the variety. So all we have to do is run another Tukey's HSD function in R and on the additive model and look at specifically the variety. So notice in quotes again, single or double. And we notice we get 3, there are only 3 varieties, therefore we're going to get 3 confidence intervals, and lo and behold, all 3 of them are significant. All p-values are significant here. Okay, so that's good. It means it's kind of backing up what we saw in our box plots. Remember, our box plot had the variety 1 was kind of like squished down towards the bottom left-hand corner, and then variety 2 was a little higher, and the variety 3 was the highest. So we're seeing that kind of play out here. And notice that all the endpoints for our confidence intervals are positive for the lower and upper bounds for the mean difference between these groups. Okay. And so that means that variety 2 bested variety 1, variety 3 bested variety 1. So that's what we saw again in the box plot. And then variety 3 was better than variety 2 by a certain margin as well. And so that's really good. And so we can make a note of that here, so that we can just say, hey, all the following p-values were significant: v2 minus v1, v3 minus v1, and v3 minus v2. So we should interpret the intervals as follows. With 95% confidence, all of the following hold. The mean citrus yield under tree variety 2 is larger than that of variety 1 by at least 3.03 and at most 21.72 bushels per tree. That came from that first significant confidence interval. Then the second confidence interval, we got that the mean citrus yield under tree variety 3 is larger than that of variety 1 by at least 22.03 and 40.72 bushels. That's quite a big difference there. So the true mean difference is quite large, even if it was only 22. And then finally, from that third interval, we got the mean citrus yield under tree variety 3 is larger than that of variety 2 by at least 9.66 and at most 28.34 bushels per tree. And so if I were giving based off both Tukey's HSDs we ran, the confidence intervals we took a look at for both the pesticides and variety, and I was supposed to be giving advice to the citrus growers that were interested in this study, I would highly recommend they grow tree variety 3 to get the most production, and either use pesticide 2 or 4 to also yield the most bushels per tree. And since these didn't interact, it wouldn't really matter whether we said that they had to do both. They could do either or, but they're probably going to get the biggest change or the biggest bulk in their bushels per tree from variety 3, and then they could also add in pesticide 2 or 4, although since we didn't see an interaction there, it's probably not going to make a big difference one way or the other, whether they use either one of those pesticides or use some other pesticide. Didn't seem to make a difference here for tree variety 3 since there was no interaction. Okay, gang, that's it for this one. I will do 2 more examples of 2 different 2-factor ANOVAs on Wednesday. I'll probably make them in separate, shorter videos and go through them a little quicker. And so one of those, the way we did this one today went strictly through that one route I talked about earlier when we talked about the steps. I will do another one that will work out this way, so you can see another example of this type of the flow of this procedure. And I will also do one where we get an interaction, where we keep the interaction term in there and we're concerned about that interaction solely. So you'll see one of those done as well on Wednesday, so you can see what to do in those cases. Anyway, I hope everybody's having a good day, and take care, everybody. Talk to you later.